In this video, we will explore Newton's third law of motion. First, the key ideas of the law will be discussed, and the idea of force pairs explored. Then Newton's third law will be demonstrated through some common applications, including rockets and multi-mass systems. Newton's third law of motion states, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. The key idea is being that the forces exist in pairs, with the two forces being equal in magnitude but opposite in direction to each other. These forces act on different objects, so they cannot cancel each other out. For example, consider a hammer striking a nail. According to Newton's third law, if the hammer exerts a force on the nail, then the nail must also exert a force of equal magnitude on the hammer in the opposite direction. This is the force pair in Newton's third law. Equal magnitude forces, but one acts on the hammer while the second acts on the nail. Note that the hammer has a much larger inertia due to its large mass, so it will have a smaller acceleration as a result of the force acting on it from the nail. Newton's third law also applies to non-contact forces such as gravity. For example, the Earth's force of gravity will pull an object towards the center of the Earth, but the object will also apply a force of gravity of equal magnitude that pulls the Earth upwards towards it. Because of the very large mass of the Earth, the effect of this force is negligible, but it does exist. For any force acting on an object, there is a second force, equal in magnitude but opposite in direction, acting on the other object. There are many examples of Newton's third law in physics, but one of the most common is in rockets. If we think about the motion of the gas in the rocket fuel, to create thrust, a rocket engine exerts a force on the gas by increasing its temperature or through a difference in pressure, pushing it out of the engine. The gas will experience an acceleration through Newton's second law, which is inversely proportional to its mass. If we switch our focus to the rocket, according to Newton's third law, the exiting gas then applies an equal magnitude force in the opposite direction of the rocket, propelling the rocket in that direction. The rocket will also experience an acceleration inversely proportional to its mass, according to Newton's second law. This is the same for any fluid being expelled from a container, such as air escaping from a balloon or water coming out of a hose. Here's an example question using these ideas. A rocket of mass 2.8 times 10 to the 6 kilograms in space fires its engine expelling gas at a constant rate of 1.4 times 10 to the 4 kilograms per second. The gas leaves the engine with a speed of 2.6 times 10 to the 3 meters per second. Determine the initial acceleration of the rocket. According to Newton's third law, the force that the rocket applies to the gas will be equal in magnitude to the force that the gas applies to the rocket. We can apply Newton's second law to the motion of the gas to find the force that the rocket exerts on the gas. Since the rocket is in space, there are no other forces acting on the gas, and the net force is simply equal to the force of the rocket on the gas, which will be equal to the mass times the acceleration of the gas. Assuming that the gas is starting from rest and that the acceleration of the gas is constant, we can use a kinematics equation to find the acceleration of the gas. Because the gas molecule starts from rest, this kinematics equation can be simplified and substituted into Newton's second law. So the net force acting on the gas is equal to the mass of the gas divided by the time multiplied by the final velocity of the gas. Note that we can group the mass and time terms so they represent the rate of change of mass. Subbing the rate of change of mass into the given equation and solving, we can find that the net force acting on the gas is 3.6 times 10 to the 7 newtons. According to Newton's third law, the force of the rocket on the gas will be equal in magnitude to the force of the gas acting on the rocket, so the net force calculated for the gas will equal the net force acting on the rocket. Substituting the known mass of the rocket, we can now solve for the acceleration of the rocket, 12.8 meters per second squared. Newton's third law can also be used to study more complicated systems, such as multiple connected masses. Atwood's machine is a common example where two masses are attached by a rope and suspended from a frictionless massless pulley. The masses are free to accelerate, with the larger mass moving downwards and the smaller mass moving upwards with the same acceleration. Let's consider the motion of each mass separately. And in this example, let's assume that mass 1 has a larger magnitude than mass 2. First, let's find the net force acting on each block. A free body diagram for each individual mass would show the force of gravity acting down and a tension force acting upwards on each block. These tension forces would be equal in magnitude due to Newton's third law. Mass 1 pulls on mass 2 with a force of tension, and mass 2 pulls on mass 1 with an equal magnitude force. We have to be careful with our vector directions here due to the pulley. When one mass moves up, the other mass will be moving down, so our vector directions need to take this into account. A good rule of thumb is to assign the positive direction to the direction of acceleration. So if we assume mass 1 will accelerate downwards, we can set down as the positive direction for this motion. This means mass 2 will accelerate upwards, so we should assign the positive direction for mass 2 as upwards. If we think about the motion, both masses are accelerating in a positive direction. Using this sign convention, the net force acting on each mass can be found. These net forces can then be substituted into Newton's second law, and an equation for motion for each mass can be written. According to Newton's third law, the two tension forces would be equal in magnitude. Mass 1 pulls on mass 2 with a force of tension, and mass 2 pulls on mass 1 with an equal magnitude force. The two equations of motion will now have equal forces of tension and equal accelerations. To solve for the acceleration of the masses, we can use substitution. Solving one of the equations for the force of tension, and then substituting this expression into the second equation. The resulting equation can then be rearranged to collect like terms, factored, and an equation for the acceleration of the masses can be found. Notice that the top of this equation features the difference in mass between the two masses, and the bottom features the total mass of the system. If instead we consider a system of both masses, with the total mass equal to the sum of the masses, then the force pair of tension would be considered an internal force, because it is contained within the system, as opposed to an external force, which is a force that acts on the system from outside. In this case, the only external forces acting on the system are the two forces of gravity acting on the masses. The internal forces of tension can be ignored. Applying the same sign convention as before, we can use Newton's second law. Note that the net force comes from subtracting the gravitational force on mass 1 and the gravitational force on mass 2. Substituting the equation for the force of gravity and rearranging, we can find the same expression for the acceleration of the system that we arrived at before. Notice that the term on the bottom of the equation is the total mass, which is the sum of the two masses. If we substitute this in, we'll get the exact same expression as we had in the previous example. This method of considering multiple masses as a single system can make more complicated combinations of connected masses simpler to analyze. For example, if we were to find the acceleration of a system of 3 masses connected as shown with a frictionless surface under mass 2, treating each mass separately would result in 3 separate free body diagrams. For this example, let's assume the direction of acceleration is counterclockwise and assign this as the positive direction for the acceleration. Newton's second law can then be applied to each mass separately, and a net force for each mass found and substituted in. This would result in 3 separate equations of motion, one for each block. This would create a mathematical problem with 3 equations and 3 unknowns, the 2 forces of tension and the acceleration. But if we consider all 3 blocks as one system with a total mass equal to the sum of the 3 masses, the internal forces of tension can be ignored. The only external forces are the force of gravity acting on mass 1 and the force of gravity acting on mass 3. Assuming the system will continue to accelerate to the left, we can set this as the positive direction for our motion. Applying Newton's second law, with a net force equal to the force of gravity on mass 1 minus the force of gravity on mass 3, we can arrive at an equation of motion for the system. To go on and solve for a force of tension, we would need to consider all the forces acting on the mass. For example, if we wanted to find the force of tension acting on mass 3, we would then use a free body diagram for mass 3 to identify the 2 forces acting on the mass, the force of tension acting on mass 3 and the force of gravity acting on mass 3. We could then use Newton's second law for mass 3 and find the equation of motion for mass 3. We would then need to substitute our expression for the acceleration into this formula to find the force of tension acting on mass 3. In summary, Newton's third law states that to every action there's always opposed and equal reaction, or that the mutual actions of two bodies upon each other are always equal and directed to contrary parts. The key ideas are that in any interaction between objects, a pair of forces are exerted that are equal in magnitude, but opposite in direction. These forces act on different objects, and so cannot be cancelled out. Some common applications of Newton's third law include multi-mass systems, where a useful method is to combine the masses into a single system, eliminating the need to consider internal forces, such as tension. A second common application of Newton's third law is rockets, where the Newton's third law force pair of the force of the rocket on the gas and the force of the gas on the rocket can be used to find the acceleration of the rocket. Thanks for watching.